So let's see. Thanks for the opportunity to present here. My name is Mai Nguyen. I'm with the San Diego Supercomputer Center, and I'm going to be talking about an approach that we have for wildfire smoke detection. All right, so as we have all heard in the news, the size and frequency of wildfires in the United States have notably increased in the last few years. So let me give you some statistics. Since 1980, 20 major wildfire events in the United States have occurred that exceeded $1 billion in damages. And 16 of those, the vast majority, have occurred just in the last 2 decades. In California, 7 out of the 10 largest wildfires have occurred in the last 6 years. And then very recently, in Texas, they experienced their largest wildfire on record, right? I think that lasted, it started at the end of February, and it was just contained this week, so just a couple of days ago. So there's a pretty staggering statistics. So wildfires can be very destructive because they can spread very quickly. Right, so as you can see in this sequence of images, the very first one, where it says fire start, that's the ignition. That's when the fire starts. And you see that it can go from something that you can't even see on an image. It can grow very large in a couple of minutes, and it can grow into a large and potentially very dangerous wildfire in just 40 minutes in this case, right? And so because wildfires can spread so quickly, early detection is essential to minimize any catastrophic damage. Okay, so detecting smoke from wildfire sounds like a pretty straightforward problem, right? But in fact, the actual task of doing this can be very challenging in real-world scenarios, just due to the nature of smoke, right? If you think about it, smoke is transparent, right? So you can see things that are behind the smoke. It's amorphous. There's no clear outline. The borders are shifting. So it's a much more difficult problem than your typical object detection problem. Smoke plumes can be very small and faint, especially if you're looking at a scene and the fire is, way off in the distance. It can be dissipating. It can move, shift, depending on the wind conditions. And there are many sources of false positives, right? Clouds, especially low clouds, fog, and haze. So we see some of those challenges in these images here. So in these images, the red bounding box indicates the location of the actual smoke plume. So in the upper left image, you see that the smoke plume is pretty apparent, right? So it's easy to pick out. But just to the left of it, there are some low clouds that look very much like smoke plumes, right? So that could be a false positive. In the upper right, you see smoke that is very faint, very small, far off in the distance. And we also see haze and a lot of low clouds, especially along the mountain ridge. And those are all sources of false positives. In the lower right, again, very small, very faint. And you see the smoke is kind of among the haze and the mist. And then in the lower left, you see smoke that is kind of against a background with a lot of glare, so it's hard to pick that out. Okay, so we have developed an approach to wildfire smoke detection using a deep learning approach. And this deep learning model we affectionately call SmokeyNet. And the architecture for SmokeyNet is shown in the figure down below. So SmokeyNet consists of 3 different neural networks. There's a CNN, the convolutional neural network, and that extracts features from each image tile. And then we have the LSTM, that's the long short-term memory neural network, and that models the temporal aspect, the change from image to image that we see in a sequence. And then we have the VIT, the visual transformer, and that captures all the spatial correlations between all the tiles within an image. So SmokeyNet is a spatial temporal model. So input to SmokeyNet is this sequence of camera images, and each image is divided into overlapping tiles that you see here in the upper left. SmokeyNet processes the sequence of images, and then it outputs tile and image probabilities. So the image probability you see in the, let's see if I can, you see the mouse? No, can't see the mouse. Okay, so the probability, the image probability is in the red text in the upper right corner above the image. And so the image probability determines the detection, right? So whether SmokeyNet thinks that there is smoke in this image or not. And then tile probabilities are the numbers within the tiles. And that indicates whether SmokeyNet thinks that there is smoke in that area or not. Okay. So to develop and evaluate SmokeyNet, we use this data set called FigLib, and that stands for Fire Ignition Images Library. FigLib consists of 315 sequences of wildland fire images from cameras, and these cameras are mounted on top of weather stations. This gives about 25,000 images, and they come from about 100 cameras that are sitting on top of about 30 weather stations. And these weather stations are scattered throughout mostly San Diego County in the remote areas. Some of them are also in surrounding Riverside and Imperial counties as well. And the time period for FigLib data spans about 5 years. Each sequence consists of images that are taken at 1 minute intervals. So these cameras that are sitting on top of the weather stations are taking images at 1 minute intervals. And what you see on the right there is an example of such an image. And the red arrow points to where the smoke plume is. So this data set has been curated such that each sequence has the ignition image and then 40 minutes worth of data before the ignition, and then 40 minutes after the ignition. So a human expert, namely Hans Werner Braun, for those of you who know him, actually went through and picked out, with the information that he knew about when the fire happened or when it was reported, indicated the image where the fire started, the ignition, and then 40 minutes worth of data before that and 40 minutes worth of data after that constitutes a sequence in FigLib. So FigLib is part of HP Run. This is a wireless network that connects remote areas in San Diego. It also connects the weather stations and the cameras that are sitting on top of the weather stations. And the data that comes from these cameras make up FigLib. Okay, so this is our workflow. This is our workflow using NRP. So FigLib images are stored in Ceph volume on Nautilus. And then these images are processed for use by SmokeyNet. SmokeyNet takes these images as input and then outputs the tile and the image probabilities. And then, of course, the results are stored back into the Ceph volume. I just didn't add that arrow because it kind of made the image a little bit messy. Okay, so we ran some experiments. Actually, we ran a lot of experiments to evaluate SmokeyNet against other deep learning approaches for object detection. So in this table here, the first entry you see is SmokeyNet. So it's made up of ResNet, which is a CNN, the LSTM, and the VIT, the visual transformer. ResNet is just another CNN. It's a bigger CNN than the one that is used in SmokeyNet. Faster RCNN and Mask RCNN are approaches for object detection and object segmentation. And then the last entry has ResNet 34 and LSTM. Those are the same components in SmokeyNet, but it doesn't have that visual transformer, so it doesn't have that component to capture the spatial correlation within each image. So for early wildfire smoke detection, good detection as well as quick time to detection are important. So that's why we report on accuracy, F1, precision, and recall, and also TTD, which is time to detect. So that is the time that it takes SmokeyNet to determine if they're, to find the smoke. So of course we want that to be as quick as possible, right? So this is the amount of time that it takes to detect after the start of the fire, after ignition. So these results show that SmokeyNet does a better job than the other architectures based on accuracy, F1, and precision. So the ResNet 50 does give better recall and a shorter time to detect, but at a very low precision, right? So there's always a trade-off. But if you take the overall picture, these results show that SmokeyNet outperforms the other configurations and delivers on high detection performance and also quick time to detect. And there are other configurations and other backbones that we looked at as well. These are just some representative ones. All right, so then once we had developed the baseline SmokeyNet, we also asked the question, can incorporating other types of data help performance, right? Help detection performance. And so we also investigated the use of multiple input data types, namely weather data and satellite-based detections, in addition to the camera image. Weather data are sensor measurements that we get from weather stations. And we use weather stations from 3 different networks: the HP RAN network, the San Diego Gas and Electric network, and also the Southern California Edison. So SDG&E and SCE are utility companies that have weather stations in San Diego County. So for every image, we get the weather data from the 3 stations, the 3 weather stations that are closest to the camera. Right, so that's what we get the weather data from. And the weather features that we use are air temperature, relative humidity, wind speed, wind gust, wind direction, and dew point temperature. So additionally, we use fire detection data that is based on satellite images. And we get these fire detections from a system we called, that is called WAFABA. WAFABA stands for Wildfire Automated Biomass Burning Algorithm. So we did not develop WAFABA. WAFABA was developed at the University of Wisconsin-Madison. We just got the data from them. So this is a rule-based system. It's not a machine learning system, and it is used to detect fires by analyzing satellite imagery. So it uses heuristics, it uses rules to determine if there are thermal anomalies in the satellite images that it's looking at. And there could be false positives here, right? So if you have a rooftop that is very reflectant, or if you have a large satellite disk, those could register as thermal anomalies as well. So the input image data that WAFABA uses comes from the GOES satellites. So GOES satellites are developed and operated by NOAA, and they're used for weather monitoring, weather forecasting. And for our analysis, we use WAFABA detections from satellite imagery from GOES 16 and GOES 17 specifically because those cover California. All right, so to incorporate these 3 different data sources, the camera images, the weather data, the satellite-based fire detections, we use an ensemble approach. Right? So we take predictions from SmokeyNet, we take weather predictions from WAFABA, and then we take predictions from a model that we train just using the weather data. And we aggregate these using various methods to do majority voting and weighted average to come up with a final prediction of whether or not there's smoke. And what we found from this was that the performance of the ensemble model was actually not much better than the baseline. And when we analyzed this, we discovered that the GOES and the weather models are weak signals, meaning that individually each one does a very poor job of prediction, of smoke prediction. And so the ensemble approach then just put the largest weight on the baseline SmokeyNet, so it didn't really improve performance very much. And so we proceeded to look at another approach to integrate the weather data directly into SmokeyNet. And this diagram shows the high-level architecture for the resulting model that we call multimodal SmokeyNet. So in essence, we inject weather data in 2 different places into the model. One is to concatenate to the CNN embedding, and the other is to concatenate to the LSTM embedding. And so in this way, both of these input sources are integrated together and processed together by the model. All right, and then we ran more experiments to evaluate how performance is affected by integrating these multiple data sources. So in this table, SmokeyNet is the baseline model, right, that has no weather information. SmokeyNet with random weather, the second model here, is using the multimodal architecture that we just looked at. There's a placeholder for the weather information, but it is just random numbers. The multimodal SmokeyNet is does use actual weather data. And so from these results, we see that multimodal SmokeyNet gives a little boost in detection performance. And it also improves on the time to detection. So the improvement over the baseline SmokeyNet here in terms of time to detection, this represents like a 14% improvement. Okay, and of course this work would not have been possible without NRP computational resources, right? So these graphs show our GPU and CPU usage in our digits namespace over the last 6 months, or at least this is what Larry told me. Right, thanks for the slide, Larry. Okay. Right, so of course training SmokeyNet requires a lot of GPUs, right? These are all neural networks models inside SmokeyNet. And the data processing and all of the supporting operations require CPU cycles. All right, so then in summary, we have developed a deep learning approach for detecting smoke plumes from wildfires. And I should have said this at the beginning, but the focus is on smoke, right? Detecting smoke and not detecting flames, because you will see smoke before you see flames. And so by the time that you see flames, it's going to be too late. The fire has already grown too large. Our multimodal extension to SmokeyNet can incorporate different data sources, and SmokeyNet provides high detection performance as well as quick time to detection. And so it could potentially be used for automated early notification of wildfires. And we also presented FigLib, which is a large labeled data set of wildland fire images. And we hope that the availability of both FigLib and SmokeyNet will inspire more concerted efforts to building tools like these for fighting destructive wildfires. All right. Right, so for future work, we would like to investigate the use of unlabeled data. There's a lot of data that are taken from these camera images that have not been labeled yet. So if we can take advantage of all of this unlabeled data, that will increase our training data and hopefully improve detection. We also want to research ways to decrease the false positives and also test the generality of SmokeyNet to other geographical areas as well as other camera types. And ultimately, our goal is to deploy SmokeyNet as an early notification system for real-time wildfire smoke detection. And I want to show you this video, and I hope it works. All right, so I'll let this go here as I talk through it. So each image comes at 1-minute intervals, right? So SmokeyNet gets each image, processes it, and outputs image probability and tile probabilities, right? And so the image probability, okay, you do see the mouse. The image probability here is shown here. And then if this probability exceeds a certain threshold, this text will turn red, meaning that SmokeyNet thinks there's smoke in the image. I'm going to pause it if I can. Okay, I think it just restarted. Okay, let's see if I can do this. Okay, so up here this is the sequence name, the FigLib sequence name. This is the time of the image. This is the date of the image. And then we also indicate here when the fire started, right? The fire start time. And then once it hits this time, that will change it to elapsed time. So the number of minutes that have elapsed since the fire started. So let me play this through, and you'll see some of these tiles will turn red. That's where SmokeyNet thinks that the smoke is in the image, and then the image probability here will also turn red. All right, so let me move this along. Right, so the fire has started, and SmokeyNet thinks that it's right there, and now you can see it. You see how it grows? And then this is it's going to grow. So it's already grown pretty large, and it's only been 13 minutes. And then the smoke will spread to other tiles, and other tiles will then turn red as well, right? But already SmokeyNet has already detected that there is fire in this image, and that was at the very beginning. Okay, so this just gives you an idea of how quickly this fire can grow, right? Right, so let me, all right, here's another sequence. So the start time is 10:56 here, and I'm gonna fast forward it a little bit, but I'd like you to kind of just try to figure out if you can detect it before SmokeyNet can detect it. All right, so the time is 10:56. All right. So 3 more minutes, 3 more slides, 3 more frames. So now you see it, right? You see this kind of smoke rising up here. But SmokeyNet, I think, caught it pretty quickly, within a minute or something. All right, let me kind of fast forward this, come to one that's a little bit more challenging. Okay, this one here, let's see, 9:48, okay. This one here is a little bit, okay, this one is a little bit more challenging. Let me back it up a little bit. You can see that there's gonna be some, let me move it forward. There'll be some low clouds that come in that look and behave very much like smoke plumes from the left here. You see that? So they start to roll in, and they look very much like smoke plumes. But luckily, in this case, SmokeyNet was not fooled by this. I mean, if I were looking at this, I think I would say that those were smoke plumes. So this starts at 9:48, but this one is a little bit more challenging. It took SmokeyNet a little bit longer to detect. Let's see. And again, see if you can try to see where the smoke plume is before SmokeyNet detects it. And it's going to be over here somewhere. Okay, so now it thinks it's somewhere there, and then it thinks, oh, maybe not. And now it's catching that right there. Okay? All right, so that is SmokeyNet at smoke detection. All right, so let me see where. Okay, so these are SmokeyNet references. This one here, the upper left is the original baseline SmokeyNet. The one on the upper right is the multimodal. There was also a KPBS feature on this. I got to talk to Tom Fudge of KPBS, if you know him, about SmokeyNet. And then we also presented this at the Neurals workshop on tackling climate change with machine learning. I think it was 2 years in a row. Okay, and then, so this work is part of Wildfire Lab, which also has other solutions for wildfire mitigation. One of those is a BurnPro 3D platform that integrates fire science and data and AI for prescribed burn planning. And of course, I wanted to make sure that I thank all the collaborators, co-authors, and acknowledge all the funding sources. All right, thank you.
Thanks very much. And so let's have questions. I mean, I'm struck by the fact that the last 2 talks, it's all about finding it quickly. And this is where so much of the change is. What's quick, of course, for Phil is way quick compared to this. But still, the idea that this is bringing in the time dimension and the pattern recognition to be able to discern something fast enough that action can be taken. That's the key difference here. And this is just to remind you, things are not, the future, the near future is not going to be like the distant past. Yeah.
I'd like to continue the time theme. How long does it take the fire people to get there? I mean, what's the ratio of the time from you get a certain amount for detection, but then you also need a certain amount of time to get the resources there to put it out.
Yeah, I don't know. I think that depends on, how remote the area is and, how quickly they can get there.
Can you speak into the mic?
I'm sorry.
Yeah.
Yeah, so it depends on how remote the area is and, how many, the resources that they have. But currently, the way that they do this is they have fire scouts just looking manually to see where the smoke is. And they also rely on reports for people calling in, 911 calls, right? And so by the time that happens, the fire can be pretty large. So, what we're hoping for is to have this be kind of an automated way for early detection.
And in fact, if we were to treat civilian threats the way we treat international military threats, you would be able to have, with the military bases we have here with the airlift capability, essentially an instantaneous response that as soon as SmokeyNet lets them know, they can have fire retardant in the air and dropping on this thing as fast as, and since we have these things very close to the areas, and we proposed this, I don't know, 10 or 15 years ago, you don't see it happening yet. So it's going to take a while, but in principle, it's just adopting a military technique against a civilian threat is completely doable. Okay, Amin. And as they say, Monty piled on. Now for something completely different. One more question. Yeah. Come on and be setting up.
Have you considered doing two convolution networks? One first to identify the sky and kind of remove the sky from the background, and then try to identify the fire?
And you'll have the whole half hour.
We haven't done that, but I think that the VIT, that's the job of the VIT, is to look at the entire image at the same time. We do some cropping to get rid of some of that stuff up in the sky, but I don't think that's actually the problem. The problem is the low clouds that are actually, where the smoke would be, especially if it's behind a mountain ridge.